So here the arch, just take an offset of it. Okay. So then I'll join these two lines. चल तो बोल बोला solid extrusion. So now we can see that this is an similarly kind of arch. Okay, so we need to check for this what is our buckling load or critical buckling load using linear buckling analysis. So same, I'll take a material of this as a steel itself. .7 this is -9. Elasticity roughness ratio is 0.3. Okay, so once the material is updated, same thing again, I'll assign a section. Now go back to assembly is a part. Next, here for the step, go for linear distribution. Here you can see that buckle, right? You can see this, right? So click on it, continue. You have two methods. One is Lancruz method and other is a subspace. Subspace is for the limit frequencies you required or mode shapes. Lancruz is used for large number of mode shapes you require. For considering, like for example, you want all the mode shapes for certain range to range. For then you can use a Lancruz method. Whereas you require 10 to 15, you can use a subspace method. So I'll request here only for 7 to 8. So I'll take 8 number of eigenvalues. Eigenvalues in the sense here buckling mode shapes. Okay. Now, if you want a maximum eigenvalue of interest, you can click here and you can write. Otherwise, not required. Now here the vector used for per iterations, like calculation iterations, how many require, that I'll take considering only for 10 is sufficient for me for each iteration of calculation. And now the maximum number of iterations you require. So what happens is, like if you take 30, your problem might not solve because the iterations to give a mode shape might take around 250 or 240. So just give us 300 would be the better. And moving to the next is a symmetric solver itself, matrix storage. So this becomes your step 1 for buckling. Whereas moving to the next is interaction. If any load or anything is there, you can use that, or else just move towards loading. So boundary condition is initial. I'll consider one end as a constraint. So encaster, and the other end I will be adding a compressive load. So you can take pressure or anything. Just I'll consider a pressure or a surface traction. It will act only on the surface. So just I'll consider this. So I'll select the surface. Now, what do you require? A shear value or a general? Here we are applying a compressive load. So I'll just consider a general value and the magnitude. So I'll apply a huge load or a very simple load like 1. I'll consider 1 as a magnitude for this. Okay. Okay. So this load is not proper one, so we'll delete this. We'll take a pressure load itself, that would be better. Select the surface and a magnitude I'll consider only 1. So why I have taken 1, I'll explain you that. So same thing, go for mesh, do the settings. I'll take 15 would be better, and mesh. Now you can see that your thickness has been, or single element has been used. If you use 2 elements, you can see capture the elements properly. Okay, so let it be this way. We'll move to the next and I'll explain that. Now go to job, create a job and give a run. That's it. So it is completed. So linear is very easy and very fast, so you can get the result easily. So now you can see your first mode. I'll just increase the port. Now we have an eigenvalues. Negative eigenvalues as -45, eigenvalue as -46, eigenvalue as 50. What does a minus value means and why? What are these values means exactly? I'll see. See, when we have added a load, that is 1, a pressure load, right? For that, for the first mode shape, how your structure behaves for the same first mode shapes, you can see that it is not pushing outward, it is just compressing itself for the pressure load for 1, which is required. If you say that your structure need to be failed for buckling, you should multiply your load with this eigenvector value, that is it is -45. For minus in the sense it has more, in this mode shape it will not fail at all, or in this direction it will not fail for buckling, minus values. Okay, so this is not a critical load or critical mode shape. Next 46, again you can see that in the same direction, in the opposite side. Okay, this is, you can say that minus 46 multiplied to your load applied is your critical buckling load, but even this mode shape or in this direction your buckling is not failing, or your structure is not failing for buckling. Moving to the third value where you are getting a positive value, if you apply that, if you apply, you multiply that value with this load factor, this we call as a load factor. That load becomes your critical buckling load. I think this third mode shape. Okay. For this, when you apply for 50, so your structure might fail for buckling. That is what this gives, and values, or what we say, a critical load value. This, I think you are not properly understanding this. You understood what exactly these values mean. Okay, I'll do one thing. We'll go for 2D elements. That gives you proper thing. The same thing I'm doing. No change in that. Now you can see this is a structure as an arch like kind of thing. Material I'll add. Here the thickness, the value, so I'll give 2 mm as a thickness. Okay, same 8 buckle mode shapes, iterations 1630, fine. Oh, sorry. Just increase this. Same pressure and consider 1, and boundary condition. Okay, so mesh, so as this has a thickness of 2 mm. Okay, so loading is wrong here. Sir? Okay. Let's check for this. Yes, load pressure is applied on the surface, not on the edge. So surface traction I will consider here. Okay, shell edge mode. Yeah. So normal. So I'll consider only this one value as 1. Go to job. ಸರ್ಫೇಸ್ ಮೇಲೆ ಮಾಡ್ಬೋದು. Now it is completed and you can see that your iterations has been calculated. Iteration is covered with value. CG mass product origin. Okay, fine. We'll see that later. So once this is completed, you can see that you have a positive value of 252.63 for the first thing, or the first mode shape. Now there is no negative value for this. This means that your structure, this structure will fail for buckling when a 252.63 is taken into consideration. In the sense, you multiply this load with 252.63, your value is getting it 1.07. It is near to 1, right? This displacement value. And if you check for the stress, stress is not there. Okay. So this 1 will be reduced to below 1. That means if it is 1, that means your structure is safe. With the multiplying this value, this will be your critical buckling load. Okay. So when you take this 252.63 complete load to the structure, your structure will fail for that buckling mode shapes. If I apply the same load as 256.63, 52.63, however we had taken the value as 1. So your critical buckling load is 252.63 in this mode. Similarly,
that means if you are applying 10 Newton means, so 252.63 into 10, that is the maximum
buckling load, critical buckling load.
It can carry. So if you got the question to find out maximum buckling load for this one, so you check all the 8 eigenvalues, which is the maximum
lower value, that will be the critical one.
Lower.
Yeah. That because
lower value will be the critical value, because that is the lower load. In case it can carry 200 or it can carry 600, this critical is 200.
For 200
so
it fails.
Lower value of that eigenvalue. So whatever you got the input load, so multiply with eigenload, that is the critical buckling load of the component.
For that particular mode shape again, that is also important. Sometimes what happens, as you can see that this shape cannot be happened. If you apply a compressive load, this might not be happen for the circular, right? Only the compressive you find a failure at the center. Same thing I'll do with non-linear, linear and non-linear both. To do non-linear, we require a linear to solve that. Okay, so this for the complete circular, when we do, you don't find this mode shape, or this load will not be a critical one. For the same thing, for the second load, second mode shape, you can see that it is in one direction, right? So as you see this, it is flowing into one direction, in negative y direction, right? So your buckle might occur with 289.81 in this direction for your compressive load. Similarly, if you go for the next shape or mode, third mode, now you can see at the edges, it is buckling at the edges. This would be the clear for you. The load is applied, your edges are getting inside. Okay, so that is the other mode shape to failure. But the critical, we say that first and second are more critical compared for the larger or beam kind of structures. Okay, so this is very simple to do a non-linear buckling analysis. So moving to the next is non-linear buckling analysis. We require, for non-linear, we require a linear buckling. First we'll do a linear buckling. We take the, what we say, geometrical imperfections, we call. For do a non-linear, we say that a geometrical imperfections will be taken from a linear buckling analysis, and that loads or that imperfections will be added to your non-linear buckling analysis. Okay, so I'll show that how we do that. Okay, so for that I am considering one of a problem which is done in abacus itself for a cylindrical circle. Okay, with that is at the end it is fixed, the above it is, the load is added, the point load or the pressure load it is added at above, with the material as aluminium and giving a bilinear curve, stress strain curve for non-linearity. And the cylinder dia is 500 and the length is 500 mm. Why this 500 and 500? We are taking a D by L ratio or L by D ratio, what we call a slenderness ratio, as 1. Okay, for that we are considering this as a thin cylinder or thin cylinder problem. Okay, it is similar as arch itself. I am just considering because I got the values, all the values for buckling, non-linearity and everything. Okay, yes, again we are using in unit ton meter mm per Newton second. So I'll just start with that non-linearity. For that, first we do solve a linear problem. Take that output of a linear, add it to non-linear. Again shell. So 500 as a diameter, as a 500 in the sense, radius will be 250. Length is also 500. So you can see that this cylinder, yes. So now for this I require 2 points to add a point loads. So what I'll do, I'll go to interaction, create prior to that everything need to be defined. Okay. Now here property, same I'll take aluminium as it is mentioned there. First thing density, second is elasticity, and then we go for a plasticity of the material. Okay, as a stress strain curve. Now you can see that what I have talked about hardening rule. The hardening rule is isotropic, kinematic, Johnson-Crook and combined. These we don't use much. Isotropic or kinematic we use more. So I am considering as default as isometric hardening rule. Okay, so if you want to know more, you just go and search why it is called as isometric and why it is called as kinematic hardening. It is wonderful topic. You can read this one. Okay, so you got all the three. So density is 7. Sorry, density he has not taken. Fine, no issue for density. I'll delete the density. So Young's modulus is 73100 and Poisson's ratio is 0.35. And going to plasticity, as it is a bilinear curve, we have only two. That is, at the yield point 1 is 160 and the ultimate is 340. At the yield, the strain value is 0, or the changed plastic strain is 0, and at 340 it is 0.3. The change in your thickness, or what we call strain value or dimensions, is a ratio of 0.3. So I'll add that 160, 0, enter, 340, 0.3. So for different material, for multilinear curve, you have more number of entries here. Okay, this is a bilinear curve, so we have took only two values. When you go for multilinear curve values, you'll have entries with more. Okay, so material has been generated. Apply the section, shell, homogeneous, and now the thickness. I'll just take as they have mentioned 2 mm, so I'll consider 2. Okay, and same thing, assign the thickness to the mid surface. Here one more option was there. As you can see that top, bottom surface, specific value from geometry or mid surface. This is because we always prefer for mid surfaces to account both compression and tension of the geometry. What happens if I take top surface or the outer surface of your geometry? It only accounts the compression. Tension will be ignored there. Okay. So always we take mid surface. Sometimes we use top or bottom because some features will be there which will have different steps. For example, how the geometry is this way and the adjacent geometry is this way. If you take a mid surface, the portion changes, right? We call this type of modeling as offset modeling. Mid surface, both are equal. The adjacent should be also in the same line. But here it is third 3/4 and here 1/4. The thickness also we need to assign in that manner as using user defined. We call this type of modeling as offset, thickness offset. Okay. So I'll consider the mid surface. Sorry, double other for the same two you have. Moving next, assembly, the same thing. Apply. Now step. So initially I'll solve for buckling, normal buckling, that is linear buckling. So for that subspace, I'll call here for 10 mode shapes or 15 mode shapes and iteration per 23. For this again I will take around 300, or you better take a higher value around 1000. So otherwise your solver get error. Okay, so just click OK. Then interactions. Why I am taking this interaction? I want to apply a point load. So for that I'll take this point as a 2 points at the center. So I'll create 0, 0, 0, 1 at the bottom. You can see that 1 at the bottom at the center, and the other 0, 0, 500 at the top. Okay. Now I'll create a rigid MPC rigids. Select a point. Sorry. only the edge. Okay, so I'll take here tie. So you can see that a tie has been generated with 1 point. Same similarly with the next. Okay, for the same cylinder, top and bottom I have taken a point 2. It will be easy to apply me load and a boundary condition. So now boundary condition for initial symmetric, only consider the bottom point constraint. Yes, same again boundary condition. I don't want my upper point to have a deflection in either direction. So what I'll do, leaving Z, the same point, leaving Z, sorry, I will arrest the entire thing. For that point, I'll add a load, concentrated load in Z direction as 1000. Okay, no, 1000, what they have taken the load or no? Okay, fine. I'll consider 1 itself, so that would be better giving an example or values. Okay, click OK. Next mesh the parts. So I'll take this as 10 mm because you'll get more features. The finer mesh, go to job, create a job, submit it. So this, once it is solved, your linear buckling analysis is done. Your linear buckling analysis is done. For non-linear, for the linear buckling analysis, you need to change a little bit. What is that? We need to add node file, star node file as U. That means your nodes displacement are required to account an imperfection of your geometry for non-linearity. So I'll show how we do that. So first we'll see what is the value we got for linear buckling, the load. Okay. load is applied in the opposite direction. Let me fill this 1 second. Go to load, so edit, so I'll take -1, okay, and I'll delete one more, just deactivate or delete completely, okay. So then go for job, create a job, so just try that initial linear buckling. It's still running. I don't know why it is taking much time. Just try for linear buckling for the same thing. ಸರ್ ಎರರ್ ಬರ್ತಾ ಇದೆ, ನೋಡ್ತಾ ಇದ್ದೀನಿ ಲೋಡಿಂಗ್ ನಾನ್ ಝೀರೋ ಲೋಡಿಂಗ್ ಅಂತ ಇದೆ, ಲೋಡ್ ತಗೊಂಡಿಲ್ಲ ಸರ್. ಶೆಲ್ ಎಡ್ಜ್ ಅಲ್ಲ ಕಾನ್ಸೆಪ್ಟ್ ಅಲ್ಲ, ಇದು ಲೋಡ್ ತಗೋತಾ ಇದೆ. ಅಲ್ಲ ಗೊತ್ತಾಯ್ತು ನೀವು ಹೇಳ್ತಾ ಇರೋದು ಅದಲ್ಲ ಸರ್, ಟೈರ್ ಪ್ರಾಬ್ಲಮ್ ಇದೆ ಅಂತ ನನಗೆ. ಏನು ಕನೆಕ್ಷನ್ ತೊಗೊಂಡಿದ್ದೀವಿ, ಇದು ಲೋಡು ಪಾಸ್ ಆಗ್ತಾ ಇಲ್ಲ ಅಂತ. Complete. So you can see that, guys. I'll show. So you can see that the buckling, it is not in a what we say geometry imperfections is more, okay, and the load what you are getting for the first state, the result time frame for the first, it is 1200, like 1200, not 5.9 as a critical load for this cylinder, for the whatever the condition they have given for this. You can write it down as 1205.9. Just note it down, this value. When you do a non-linear, compare the value for the same thing. For here it has not taken any of your non-linearity here. Okay, so you understood this. Everything is same. I have not changed anything. Only now for the non-linearity, what we need to do is, like, for the same thing, edit keyword is there on the model. If you go and click on the model, there is an edit keyboard. So it will open your deck. Whatever you have done, it will open your deck. So here your deck starts from the part, and element type is S4R, section, thickness, and when it comes to assembly, your instance has been created, instance is ended. Sorry, you have created MPCs, 2 MPCs, that assembly is being completed, material is given. If any changes you want to do, you can also change into this, that is your text format, what we say as a deck. Okay, so now boundary condition star step is started, star buckling. We are requested for 15 mode shapes, and iterations are 23, and the iterations can be taken up to 1000. Okay, so boundary condition encasted, we have given load, we have applied a C load, that is point load, as a 1000 downward. Okay, 1000 load is at downward. That means your load is 1000 into 1205.9. So that load is for your critical buckling, for the buckling load. Okay, now what we require to request for non-linearity to get the geometrical imperfection is, just enter star, I have written it, node file, enter U, capital U. You can see this, star node file enter U. Okay. Once this is done, as I said, star will read your file. That means this will write for the forces, or the what we say, for each node a separate file called as node file. Okay, so that we are requesting from linear buckling analysis. Okay, so now I'll go back again to job. I'll submit the job for run again because I require node file, which will be called for non-linear analysis. So once this is done, so for the same job, I'll copy that model. So this is done now with node file. So at the same location, I'll not change anything. What I'm doing, I'm copying this model as model 2 non-linear. Okay. So as you can see that there is model 1 which is linear. I'll rename this as linear, and the second model is non-linear. I'll go to second model. It is same as linear itself. Now I'll change here. I'll go back. I'll change for step. Sorry. I'll go for step. I'll delete this step. Okay. I'll delete this and I create a new one. What is that new one is? It is static risk. It is a static risk. So that means it does a non-linear buckling analysis for static load. Okay. So static risk, continue. Again, here you need to on LM geometry, NL geom. Okay. So on that. So again you can use maximum load proportional factor or degrees of freedom, anything. That is fine. Go to increments. A number of increments required. So how much time you require to solve your problem. So I will take this as each step, minimum step as 0.001. 001 as an initial step, and maximum step I'll take just 1000 steps are sufficient for me as a maximum, and number of increments I'll take thousands. Okay. So estimated arc length, let it be 1. Use default. Everything will be a default one. Okay. So static risk. Enter. Now go back to loads. Check the load is there or not. It has been deleted because it was for that step. So create it once again at the top as a point load for the step 1 as minus 1000, right? We have taken a same 1000 load. So click OK, close. Then check for boundary condition. Boundary condition is there because we have created that for initial. Next, mesh is there. If you want to find mesh, so you can do it so that you can get more clarity on the load path job. Again, this job I'll delete this. Okay, so I'll create a new one as non-linear. As a non-linear. Continue. Okay. So this job is created now. Prior to do that, I'll call the file which I have taken from the linear analysis. Right click, edit key attributes. Your deck will create for that. So now you can see that Your star step has been created. Star has static risk. Your time increment, initial time increment, and final increment is 1. Steps are 1000. So load is given. Everything. Here again, what I'll do? I'll delete this. 1 second. Hello. Wednesday, joining here. Nineteenth and Telegram. Packaging. Packaging. Okay. Okay. Okay, sir. I can join on Wednesday. You don't. Sorry. Discuss with the salary package. Let them. First you said I'm okay that, but I'm looking for the package. So what is an offer I am getting? Fine then, fine. Just okay. Sorry for that. So what we need to do is we need to add one more line, that is star imperfection.